Hey everyone, it's Bailey and Brooks. We are here to talk about our talks from DevOps Day Nashville, which was last week. I think we had a pretty good time, didn't you, Brooks?
Of course, I was muted. Yeah, it was a lot of fun. We got to go out, met a lot of really interesting people there at the conference. We ate hot chicken, I think, every day, which is a lot of fun. Hung out on Broadway. It was a good time. I was glad to be there.
Yeah, hot chicken for breakfast was probably my favorite part. Hot chicken and waffles. Yeah, we had a great time. The talks weren't recorded, so we thought, hey, we did all this work prepping for it. We might as well give it again and record it this time so other people get a chance to watch it. Because we've got a whole different set of talks that are going to happen literally next week, which I can't wait to watch Brooks talk. Personally, Easter eggs. There's a poem involved. It's going to be so good. So let's go through our first set of talks. Mine was an Ignite talk, which means, and I didn't figure this out until a few days before I actually gave it, but it means basically auto-advancing slides with 15 seconds a slide. So I'm gonna give my talk first out of the stream, mainly because hey, it's so fast. But I will not be auto advancing because that was really stressful. But also, if I can sneak in a few extra sentences here and there, I think that clarifies things a little bit better than the original. But I didn't change the content, and the slides are the same. So you're basically getting the exact same thing, but like without me having all of the frantic energy that I had before. It's good and bad. You lose a little bit, you gain a little bit. So it's called Wasm Whirlwind. Can you see that okay, Brooks? It looks good.
Yeah, I was trying to figure out if there was a way to set up a timer, like a 5-minute timer to hold you true, but
Gosh,
just have to
no.
trust you.
Just trust that I'm gonna go to 7 minutes. 7 or 8 minutes, I think, is what I'm expecting. So, all right, I'll kick it off. This is a whirlwind tour of WebAssembly and how it's taking off as a cloud native technology. And hey, I'm Bailey Hayes. I'm a director at Cosmonic. I am also a hardcore Wasm enthusiast, and I've been lucky enough to have Wasm be a key part of my technical stack from as early as 2012, if you count WASM.js as the precursor to WebAssembly, and in 2015, if you'd rather just start with WebAssembly design proper. Now, I called this a whirlwind tour, so this is your first gust. WebAssembly is neither web nor assembly, and the reason for that is that it's an assembly-like language that many different languages can target, and so from this point on, I'm going to call it Wasm. You can call it Wasm or Wasm. That was one question that we got at the conference. Either way is fine. But this compilation target can run anywhere in the web, on a server, or on the edge. And it's portable, secure, tiny, like very complex, compact binary format that's really fast to download and start. You can even begin compilation as it's being downloaded, so streaming compilation. And all of these different properties make Wasm particularly well suited for the cloud. Wasm became a recommended web standard by the W3C in 2019. That's also when the Bytecode Alliance Foundation was founded. I'm on the technical steering committee for the Bytecode Alliance, so a little caveat there, disclaimer, but it's got a lot of amazing projects, including WebAssembly runtimes, SDKs, and all of that to make it compiling and running Wasm as safe and easy as possible. Two WebAssembly runtimes that are in the Bytecode Alliance are WasmTime and Whammer, and they make it really easy to run in the cloud, also in databases embedded, and in embedded devices, so even in very tiny places. Docker also supports running Wasm. Docker actually has it where you run as a target and you target a Wasm runtime directly rather than just in a container, but Wasm also runs great inside a container as well. There are many different ways to run in Kubernetes. One of those ways is with the containerd run WASI shim. To understand what that is, you need to know what WASI is. So WASI started as the WebAssembly systems interface. We also started talking about this back in 2019, but really now it's kind of changed over time to become a set of high-level APIs, and so I think of WASI as really WebAssembly standard interfaces, and those standardized APIs are things that many different WebAssembly runtimes support. And the reason why you need WASI is that really a WebAssembly module is a bunch of numbers in a trench coat. That's how I think of it. It can't really do anything unless the host gives it a function handle that it can call. Other key properties of a WebAssembly module is that it's typically one binary for an entire application, and it is usually built from one target language. Now, the WebAssembly WASI APIs, that arrow there is really what I'm talking about for that function call that the WebAssembly runtime provides. And that little function call gives a lot of different capabilities like networking and file I/O. There's also something that we've been working on over the past couple of years that makes Wasm even more powerful, and that's called the component model. The component model is a design for an updated Wasm API that makes it really easy for us to assemble a Wasm component and treat everything it needs for a specific platform. So we can target things like making it run even better on IoT versus running in the cloud. So that's what that platform virtualization or platform layering bullet is for. And also we can treat Wasm components as libraries and makes it really easy for us to cross language boundaries. So now instead of having, say, one .wasm, I can have multiple .wasms that I link together, and one could have been from Rust and one could have been JavaScript, and then I can have a completed component that combines the best properties of both. And I expect this to change the way that we write software today. Wasm components will be GA. GA is a little strong. It'll be available with WASI Preview 2 in the fall. That if that sounds kind of far away, well, standards aren't known for their speed, so, hey, stick with us. But there are real implementations of this today, including the project that I work on is wasmCloud. Now, at this point, you're probably wondering, why did I give this talk at a DevOps day? And so here are some of the beats that we're all familiar with. Most of our applications today are made up of other people's code and all of these non-functional requirements as dependencies. And a stat that I found really surprising is that 87% of containers that are in production today contain a critical or high CVE. Now, that means that everyone, all of us, share this burden of having to maintain our software and update our dependencies frequently to prevent vulnerabilities and software supply chain attacks. And all of that churn is really not related to shipping new features. It's really just to maintain that one feature of our code, which is security. So the question is, how do we find ways to eliminate that churn? And so let me introduce you to the 4 horsemen of development. There's a lot of things that go into working on a new piece of code beyond just the construction, just building and designing a new app. You also have to think about how it fits into the existing architecture. And our architecture today may involve thousands of microservices. And that maintenance cost that I talked about, you don't just update to the latest version, you need to also update to like the latest supported version. So you need to deal with breaking changes between minor revs and major revs so that you're using a version that is continuing to get patch updates. And then also when we build our apps today, we typically have a build matrix of many different operating systems and CPU architectures that we're targeting. And with Wasm, because it's a portable compilation target, we're able to target just one target. So you can eliminate that giant matrix of things that you have to build, test, and maintain to just one thing. And that can really help. Something else that I believe will help a lot of developers is the WebAssembly Application Runtime, which is wasmCloud. And that makes it really easy to orchestrate Wasm, but it also helps us decouple dependencies and allow at runtime updates of the platform. And we also do this with distributed capability providers. And the secret sauce for all of this is that it's built on top of NATS. And NATS gives us this flat network topology that's self-healing so that we can distribute our applications both from the cloud to the edge where our users are today. So if you're wondering what is a Wasm component, what does it look like? Well, here's all the source code you need to have one component. The important parts here is really what's missing, and that is I'm talking to a key value store and a messaging provider. But typically when I look at an app that's written today, I would have an import here for, say, Kafka for my messaging part, and I would have an import maybe for Amazon DynamoDB, a different type of key value provider. And so I've got maybe some boilerplate code that lets me connect to those different capability providers, configure that client, and then establish that connection. But if I'm writing a Wasm component, I really am able to kind of just target this high-level API and not worry about all of those other different types of details. And this is written in Rust, but it could have been written in any language that supports a Wasm component, which could be like JavaScript or Go. Now, to run this, it's really, when I go back to saying it's just a compilation target, again, target wasm32 WASI. We do a step here where we upgrade that target to a component, and then we deploy that to OCI. Now, I'm showing a visual here of within Cosmonic, which is a PaaS for wasmCloud, which gives us a very pretty visualization of this, but don't worry, there's a declarative manifest, so your YAML is still there if you want it. With this view, what I'm really showing is that I initially linked to Nat's Jetstream key value provider, and then I relinked it to a Redis key value provider, and then later Vault. And there could be many more. Anything that matches that key value API is now something that you can add to your stack. This is really powerful if you think about, say, Redis has a vulnerability, and I need to upgrade to a newer version of Redis. I can relink it at runtime without recompiling and redeploying my application. Now, that means that I can make this type of thing a thing of the past, where DevOps practitioners and platform teams can focus on the capabilities that the platform stack needs, and we're focusing on maintaining that one thing that needs to change, updating the dependency, say in that last case, Redis, and not on rebuilding and redeploying the entire world like what we do today. And all of that is enabled by using portable Wasm components that are signed and sandboxed with decoupled capabilities. And all of this lets us reduce those 4 horsemen of development. Now, by eliminating boilerplate and letting devs get back to focusing on writing just their business logic, we can really change the way that we write software today. We've spent the last 10 years figuring out how to containerize our applications, and now I'm asking you to figure out and join me in finding ways to componentize them. Thank you. Join our community. All right, Brooks, you're up.
Nice job, Bailey. Yeah, that's great. It's actually kind of nice. I did have a lot of fun watching you do the like 15 seconds auto advancing, but it does give, I can see where it gives you just a little bit more time to elaborate on some key slides.
Yeah, I wonder in the 5-minute one if people even had a chance to read the slides, if they were listening to what I was saying. So yeah, I held it a little bit longer for each one, but content was the same. So nobody missed anything, I don't think.
Nice. Yeah, we had one question on YouTube, which was just quick. I couldn't show it here, but I went ahead and answered it. It was what is a CVE? You know, I didn't know the acronym Common Vulnerabilities and Exposures. Bailey, what I said is that it's just basically a standard format so that we can, and by we I mean technologists, we can report security vulnerabilities with a severity, remediation, effective versions, all that kind of stuff. Would you add any more information there?
Yeah, part of the reason why we came up with a standardized format is it's something that everybody across the software industry is looking at. So we kind of have the exact same standard for, okay, when do I need to update this? How bad is it? And if it's a high or a critical, it's pretty bad. The critical is the highest, right? And what that basically means is that maybe there's a 0-day vulnerability, there's a known exploit, or it's something that somebody could easily put together and begin exploiting applications that are out there. That's a critical. So that's a big deal. Highs, there's a chance in the high that maybe like it's not possible to mess with the application, but it's bad enough that we want to fix it ASAP. And so at least like at past companies that I've been at, we would have a rule that said if it's a high or a critical, we need to fix it in a month, which sounds really long. A critical needs to be fixed ASAP, like that's a war room type situation. But a high is typically like, okay, I would write up a thing that as the platform, one of the platform engineers, I would send a thing and be like, all right, everybody, we are updating all our dependencies again. And then I would generate an SBOM and I would audit all of our dependencies and make sure that everybody has updated and there's not some like third-party dependency that's causing us to stay back on that older version. And it was a big lift. That a month was actually fast. A month is about how long it took for hundreds of microservices to get updated and get audited and all of that kind of work. So like when I'm talking about churn and eliminating churn, like I'm talking about like just for the environment, it's a big improvement, because turning that software crank for a giant, just a mid-size company was really, really expensive. So I hope that answers that question.
Let's see. Just do a little double check. Looks like you got a heart for your answer, Bailey. So that's good. All right. Well, feel free to, whatever source you're watching on, feel free to drop a comment. We can get to it. I'll probably just look over. Bailey, you can interrupt me, but I guess I'll go ahead and get started on mine. Aha. Okay. So it came up right away. Nice. I'm glad I didn't do it in the middle. All right. Well, hello, everyone. This is going to be my talk was a little bit of a longer format, around 30 minutes. It might be a little bit quicker today since we're doing it back to back. There's some information I won't double cover, but the title of the talk was Cloud Native on the Edge. It doesn't have to be hard. And I was really, I really liked presenting this one. So I guess I can do a quick introduction, even though, it's kind of already been done. Software engineer at Cosmonic. I've been working on wasmCloud for about 3 years now. And of course, I'm a demo enthusiast. You're going to get to see some demos in today's talk. So as far as what I'm going to go through, I'm going to talk a little bit about what is WebAssembly. And in this stage, I'll probably go through a little quicker since you probably just watched Bailey's talk, but I'll get the basic info and talk about where it fits into the cloud native ecosystem, do a couple demos on the edge, and then talk about what you can do now with WebAssembly, wasmCloud, and how to get involved. Same kind of thing. So you saw this slide in Bailey's talk. We love this slide, neither web nor assembly. But what I really like outlining for this is why, like what the motivation for WebAssembly in the beginning was. And it's a little bit of an oversimplification, but really what it came from is the desire to run native code in the browser. There's a lot of really impressive libraries and functionality that are implemented in C, C++, essentially code that we run on the server somewhere. And if we could take that and at least run part of it or all of it in the browser, that would be huge. We can take things like encryption libraries, things that are performance sensitive, things that basically we don't want to have to rewrite in JavaScript, and move that to the web. And so, this slide is all about what did it have to be? What did WebAssembly have to be to make that happen? It's an open W3C standard, so it's the 4th language of the web, same standards body that represents and develops HTML, CSS, and JavaScript. It needed to be safe and secure with a deny by default sandbox. You can't just have native code going and forking off processes or opening network connections for free. It needs to have a capability driven permission model, just kind of like the browser works today when you visit a website and it says, hey, can I please access your camera, or can I use your microphone, things like that. It needs to be efficient. There's no point in taking native code and running it in a ridiculous emulator that's 1,000 times slower in the browser. It needs to run at near native execution speed, and it needs to be small. There was a study that I found from Google, actually, that if it takes more than, I think it was 2 or 3 seconds for you to load a web page, over half of the people will just leave. They will not stay. They will go to a different website and not come back. So you can't just ship around 100 megabyte binary around as WebAssembly. Given the fact that it's going to run in the browser, the nature of it being polyglot actually comes along with that. So in order to run in the browser, it can't be dependent on a specific operating system or architecture, and it can't be something that can only run in one area. So you can't only run it in Chrome. It has to be able to run in Chrome, Firefox, Safari, all of these different web engines. And so the format that it needs to compile to is just a compile target. It's not necessarily tied to the source language, which is awesome because you get to kind of write in the language of your choice. And I kind of touched on the portability, but WebAssembly does run in all major browsers today. That support has been shipped since 2019. I believe Bailey can jump in and correct me if I'm wrong. So all of these things, when we're thinking about what WebAssembly needs to run in the browser, really apply very well to server-side development. These are things that we want to come out of cloud or edge or server-side programming in general. We want it to be safe and secure, deny by default. We want it to be running at near native speed, even with a small level of abstraction. We want our binaries to be really small and efficient, and we want to be able to write in a language of our choice. So when I talk about WebAssembly, I really want to nail home the point that it's not specifically tied to the web, and it's not an assembly language that you're going to have to learn and get used to. It is a compilation target that you'll write code in the language of your choice and compile to WebAssembly in order to make server-side programs, which is really fun. Now, I've started talking about some of the domains that WebAssembly is really, really good for today, and then some domains that it's not so good for. And I put good versus bad as a contrast, but it's not to say that WebAssembly will forever be bad in this second area. Just want to draw the contrast between the two. So WebAssembly is fantastic for general server-side computing, the microservices or functions as a service style functions. Those things where it needs to instantiate quickly, execute, and then exit, and then optionally clean up to remove the resources. WebAssembly is really fantastic at that. Essentially zero cold start time in order to instantiate a WebAssembly module. It's very efficient. WebAssembly, the nature of portability and its size is great for constrained devices, or very nebulously, the edge. Things that are not running with a full supercomputer, or not really supercomputer, but like the laptops that we have today, it's something that's less powerful than a cloud machine. WebAssembly is fantastic for plugins, things like filters with Envoy, or user-defined functions in Single Store, or user-defined functions in e-commerce with Shopify, things where you want to be able to run user untrusted code really close to the data without compromising on security or speed or the ability for your users to be happy and actually contribute those things. So plugins are a fantastic use case for WebAssembly. It has the potential to be one of the last plugin models. Lua has been very successful in this space, so keep an eye out for that. You can runtime optimize the way you want to run your WebAssembly module, so it really lets you tune performance down to a small level based on your use case. Great for writing libraries that can be connected and programmed into other programming applications. And of course, it's fantastic for the browser. You've seen many successful cases of WebAssembly like Google Earth and Adobe Photoshop and the web and Figma. All of those things use WebAssembly as a core thing to their product. Now, the bad things, the things that WebAssembly still has some rough edges around today. Networking is still difficult. It's going to be really hard for you to take a library that you're used to using to do networking and compile it straight to WebAssembly. That has mostly come out of the fact that the standards are still really in the fast moving stage. So things are changing all the time. Proof of concepts are being updated. And this will all, of course, settle down a little bit over time, but it's worth mentioning. If you write a WebAssembly program using Wasm today that does a network call or accepts a socket, it is likely to be different over the next 6 months, over the next year. And so working on the bleeding edge, just prepare to get cut a little bit. And this doesn't mean everything's going to change and be ridiculously different, but you might have to recompile your application at some point. It is a little slower than native code. The last study that I remember reading is that it's approximately 3% slower than running native code. But you pay a penalty for any level of abstraction that you have in your program. So running a little slower is really eclipsed by the time it would take to make a network call over the time it takes to just process something in memory. The concept of doing a lift and shift isn't quite there yet for WebAssembly. With containers, there was this accessibility where instead of compiling to a native binary, you could essentially compile to a native binary inside of a container that has a full operating system and kernel for Linux available to you. But you can't really do that with WebAssembly. It's likely that you're going to have to modify an existing application in order to compile it to that target. And some domains, some applications are probably just not going to be rewritten to WebAssembly quite yet or for a long time. Things like Redis, Nginx, MySQL, These are essentially picked out of a hat. I have no idea what these applications' actual plans are for if they want to add WebAssembly support, but I'm just trying to pick them as an established, long-standing application that does a really good job of what it's doing right now, and portability is not really the biggest concern. One other thing that it may not quite work for as a domain is if you're writing code that's specifically tied to a CPU architecture or a specific operating system, the abstraction that you have with WebAssembly will probably make your life harder, because if you're doing something specific with Linux, then you should be running the binary on Linux. It shouldn't be through another level of abstraction. Now, those are the things with WebAssembly, and there's a lot of really awesome benefits to the technology at its base. So I'd like to transition a little bit into talking about wasmCloud. This is the open source project that I've been working on even before I was at my current job. It's been open source from the start. It is a CNCF application runtime. It's at the sandbox level in the CNCF, but the reason why wasmCloud exists is for creating applications. It's that higher level abstraction, the SDKs, the runtime level of that makes it perfect for writing WebAssembly applications that can be distributed, that can be run in the cloud or on the edge. And a really key thing to kind of tie this together is thinking about writing a web application. You wouldn't just bust out all the raw HTML, JavaScript, CSS. Nowadays, you would likely use something like Vue or React or Angular in order to create a web application. If you're creating libraries, of course, it's different, but creating a full application, the internals and the lower level interactions with a WebAssembly engine or the interactions with like importing and exporting functions can be a bit clunky. And so using a higher level application runtime like wasmCloud, it's not the only one, is generally a better way to go. So for those of you who aren't familiar with wasmCloud, I like to explain it in a couple of different layers. This is a cloud native technology. And at the base level, we are running and orchestrating WebAssembly modules. It's your core application components that you implement and compile the WebAssembly. wasmCloud gives you secure access to application level capabilities like HTTP servers, key value stores, message brokers, secret stores, all kinds of things like that are all represented as capabilities, especially things that access state. And due to the way that it's designed, we also manage the networking, failover, and request routing between services. And you can run multiple wasmCloud runtimes and multiple WebAssembly modules inside of those runtimes in order to manage a couple of different dimensions of scale. Now, the reason why I call this a cloud native technology, of course, this is completely designed in the age of the cloud. But we also build on top of all kinds of different existing standards to make it easy to integrate into existing applications, workflows, tools, things like that. All of our WebAssembly modules that we distribute, we do so with the OCI or Open Container Initiative spec. We push WebAssembly modules up to container registries like GitHub Container Registry, Azure Container Registry. And it's not actually built into a container. It's just the WebAssembly module with a custom type, but that's getting into the weeds. Essentially, we're just using the distribution standard that people already are used to using for containers. We use the open application model for all of our declarative application manifests with WADM, with the wasmCloud Application Deployment Manager. Everything that happens in the system that's significant, we publish as a cloud event, which you can subscribe to and essentially build up a view of what's going on in your wasmCloud network. The entire networking layer is managed by NATs. So it's all the way down pub sub messaging. We're using Jetstream for persistent stores, things like that. And everything in the wasmCloud ecosystem is instrumented with OpenTelemetry. So you can start the wasmCloud host, give it an OTLP endpoint, and you can watch the traces flow through the system, no matter how many different WebAssembly actors or capabilities you have. Now, these WebAssembly actors, this is what we call our WebAssembly modules. It's where you implement your business logic in terms of common contracts. So when I talk about capabilities, things like HTTP servers or key value stores, here you're working in the language of your choice. You're using SDKs in order to interact with abstractions. So for a thing like a key value store, the implementation may be Redis, but at compile time, when you're building your application, you're just talking about a key value store, a key value sender. And using those abstractions allows you to run these WebAssembly actors anywhere, take advantage of their tiny footprint and deploy them to smaller edge devices or even run it in the cloud. And then they can access state through these capability abstractions. Now, capabilities are implemented as native binaries that we run on the host. wasmCloud implements many of these and provides them in the open source, so you can get started without implementing your own capabilities, though that's always there. And this is where the implementation of these capabilities comes in. So you're bringing in open source libraries, you're connecting to different databases or making HTTP requests with TLS, things like that. All of that is done abstracted away from the actual application. So for many of your first wasmCloud applications, you won't even need to worry about the implementation itself because it's already been implemented before. We've had a couple community members implement some capability providers. That's been really exciting to see. But that abstraction, essentially what Bailey is talking about, where there's application vulnerabilities, instead of 100 different microservices having the same library and updating that, trying to redeploy everything like that, that all goes into a capability, can be upgraded once by a platform team, and then all the applications can just live relink to the capabilities. Really nice. Last but not least, we have our wasmCloud Lattice Network. This is implemented with NATS under the hood. The NATS is a CNCF incubating project, but it's they call it connective tissue for disparate applications, I think, something like that. You can see it on nats.io. It essentially allows us to have a flattened topology network where no matter where our wasmCloud resources are running, they can always connect to each other. They're dynamically adding and removing at runtime. You don't have to do a formal clustering policy or know or deal with IP addresses. All of those things are all handled by NATS under the hood, which is really nice. Now, where we see WebAssembly and wasmCloud fitting into the whole cloud native ecosystem is somewhere at the end of this graph. Over time, we've seen this trend of reducing the responsibility of the developer and further abstracting away the platform from the actual application itself. So as we've gone from imaging an entire PC to creating VMs in the public cloud to abstracting away the kernel with Docker, you can see this trend of lower and lower responsibility and greater portability for your applications. Now, running in containers in Kubernetes does a really good job for a lot of the applications that we're running today, but we're still dependent on the platform. We're still dependent on a Linux-like kernel. We're still dependent on running your actual container on the Linux operating system. And so WebAssembly fits in by bringing that level of portability, the true platform and OS agnostic portability to your application. Additionally, the deny by default security model gives you something that you can't accomplish with containers today. Most of the time when you develop applications with containers, you give it all the capabilities in the world to make it work. And then eventually, once you end up deploying to a different environment, you add on layers of security on top of that. But that really creates a brutal model where it's difficult to fully lock down an application. And let's be honest, a lot of developers don't really care at that point. They just want to write their application logic and deploy it and let it go. They don't intentionally want it to be bad, but you know what I mean. Now, wasmCloud fits in right at the end of this graph only because of our opinionated way of separating applications from their capabilities, their non-functional requirements, or the implementation details that we really just want to pick at runtime. With wasmCloud, all of those libraries are abstracted away from the application as well, so that you can write in terms of pure logic. And then your application doesn't need to change when you change implementations or you change what cloud you're going to run in. Or if I take my application and I run it on a Raspberry Pi instead of my MacBook, I don't need to care about any of those actual runtime details. I get to configure all of that, and my application doesn't need to change at all. So this is a really, really powerful graph when you think about kind of the trend of how we have cloud native development at all. Now, I have one more slide before I actually get into demos, and that's just to at least clarify what I mean when I did the little air quotes, the edge before. Now, people, depending on who you're talking to, people have different definitions of the edge. And when I talk about it, I'm at least just talking about the compute that's outside of a major data center. So outside of a cloud provider or running on your own, like running on your own on-prem data center. I'm talking about running on tiny devices, things like Raspberry Pis with like half a gig of memory, or things like you're trying to run as close to the data as possible. So if you're running on like a point of sale device, like a cash register in the store, that's an edge device. Like that is something that you're trying to basically push compute out as close as possible to make it run as efficiently as possible. So that's what I'm talking about when I say the edge. I can't solve the whole buzzword thing now, but we'll see where that goes, especially with some of the big work that's going on in the edge SIG in the cloud native landscape. All right, that's enough of the slides. I want to go ahead and get onto the demo. And what I'm going to do is I'm going to show an example that if you're in the wasmCloud or Cosmonic ecosystem, you probably have seen it before. It's our key value counter. This is a really simple microservice. It'll be pretty familiar if you've ever written like a serverless function before. But the requirements for it are that it takes an HTTP request and increments a value in a key value store, persisting that data and then returning the new value as a response. So at the base level, you can imagine the logic for this application being really, really small. And what I've done with this little application diagram is I've broken out the pieces of what this application needs into the wasmCloud terms. So we have two capabilities, the HTTP server and the key value store. We'll get to actually pick the implementation of that at runtime. And the part in the middle, the actor, the WebAssembly module, is our pure logic. So taking the request, thinking about incrementing something in a store, and then returning a JSON response. That's our business logic. Now, if we take a look at the actual code for this application, let's see, that should be good, but I'll zoom in a little bit more. If we take a look at the code, what this actually looks like, and this is in Rust. We and I write most of my WebAssembly modules in Rust just because it's my language of choice, but this will be definitely easy to grok even if you haven't before. We have one trait, which is kind of like an interface in other programming languages, called HTTP server. We implement that trait. It has a single function called handle request that takes an HTTP request and returns an HTTP response. So this is a high-level abstraction of what an HTTP server is. This actor is acting as that HTTP server. And you'll notice if you look around the code, there's no mention of how we're going to get that request or where the response is going to go. All of that is implementation detail that we can figure out at runtime. We can let wasmCloud handle for us. So we do a little path matching, try to make sure if we get a GET request to the API, then we increment our counter. And what that function actually looks like is using this abstraction called a key value sender, saying, hey, I'm going to send a request to a key value store. Just please increment the value at this key with a value of 1, and then take that resulting value and return it as a JSON blob and an HTTP 200. Right? This is the logic for our application, and you could code this up in a matter of minutes just given the requirements. Now, what you'll notice is not only is this whole thing 49 lines, which even includes some special sauce for I'll show you in the demo, but there's no mention of what specific implementation we're going to use for the HTTP server or the key value store, which is very powerful. Given that flexibility, being able to pick that out at runtime actually enables this whole demo to work. So without further ado, let me show you the key value counter. This is it. The little special sauce is just that we added a couple UI static assets to actually make it look fancy. You can launch off fireworks, all that stuff. But this is how it works. You click the increment button, sends an HTTP request to our key value actor, and then increments that value and returns it as a response. So you're kind of seeing both ends of like the client and the server here, but all in the same WebAssembly module, which is really cool. So this is the key value store. If you're astute and have maybe magnifying glass or your zoom in goggles, you could see that this is running on localhost. And if I take a look, I'm actually going to show you this inside of Cosmonic. It's just for the visualization. You can actually see that this entire key value counter application, I've essentially got hooked up to two different capabilities. I've got one HTTP server that's running on my local machine, so like this MacBook that I'm presenting from, and it's connected to a Redis key value store, which is also just running on this Mac. And we have one key value counter actor that's running locally. So this is great. I've got everything running locally. It's working. And if you think about the journey that you usually take to take a containerized application from development to production, you can think that actually deploying this into the cloud will be a huge pain. It's something that is going to take a lot of effort and is not going to be easy. But what I want to show you is that journey with wasmCloud. So let's take this application and move it onto AWS, which is just the cloud that Cosmonic runs on. Let's move it to AWS live and one at a time. So the first thing we need to do is create a public endpoint. What we can do is, since we have this key value counter hooked up to a local HTTP server, we can just create another link to the managed HTTP server, which is running in Cosmonic. And what that can actually do is spin up a DNS name, give you a public endpoint for you to hit this actor. And just by reconnecting that, just by giving the wasmCloud runtime instructions for where to send the HTTP request, you can actually hit a public URL to get this actor. And now I'm going to do something really quick while I give a little bit of a spiel. This is a QR code. If you're watching the stream and you want to scan this, or you go back and you take a look at the URL, you can actually go and hit this application for yourself. That's actually sending the HTTP request from your machine to my public endpoint, and then all the way down to a WebAssembly module that's running on my MacBook. And I didn't have to do anything with my firewall or anything to get that to work. It's just the wasmCloud Lattice Network. So I'm going to get back to the demo. I guess you can go ahead and rewind if you wanted to access this if you missed it. Now, the next thing is that we probably don't want to just be running this key value counter on the local machine. Actually, I'm kind of curious if anybody hit it. Nope, it's okay. We probably don't want to be running this key value counter just on my local machine, right? We want to be running that in the cloud. Now, I actually started this from our wasmCloud Azure Container Registry, just running as it's a WebAssembly module in an OCI registry. And I can start another instance of this actor on a Cosmonic managed host, so starting it in AWS. So doing that, I can now see that I have one running on my local machine unmanaged and one running in Cosmonic. And if we go back and we hit, hey, nice. If we hit this actor, everything is going to work the same, right? We'll have additional things because people are hitting the QR code, but everything is working the same. And that's actually, it's not exactly always forwarding to one or the other. It's actually kind of live round robining those requests. But of course, you as the consumer don't really care about that. Now, the next thing is that we probably don't want to always tunnel the request down to my local machine in order to store that data in a key value store. Store it in Redis specifically. We want to be launching that database, storing it in some kind of cloud persistent store. So what I can actually do is I can terminate the link between KVCounter and Redis. And if you go hit the application now, you'll notice that it's broken. I've removed that link, that instruction to say, hey, send key value requests to this data store. And we can hook this up to the NATS-backed Jetstream key value store in Cosmonic. If we go back and hit that application, of course, the number is a lot bigger because I use this one for a lot of demos. But now we have essentially taken our entire key value counter application and live rewired it from running on my MacBook to running in the cloud. So I can even come to the infrastructure view here, and I can find my local wasmCloud host that's running on my machine, and I can just completely terminate it out of the Lattice entirely. So now the place that my application was fully running before is no longer alive, and we can actually hit it as if nothing had changed, and that's because we're able to dynamically rewire that to run in the cloud. And this is really just a testament to the flexibility of WebAssembly and the concept of wasmCloud's Lattice Network with these common abstractions. The ability to do this is really a breath of fresh air when it comes to modern development. And it's really fun because I can develop this WebAssembly module locally, and I know that it's not going to change in terms of logic by the time I deploy to the cloud. So very fun. I'm going to go back to slides really quick. I've got one more application that I like to show, and that is very analogous to a kind of a famous application example. I sometimes question how many people have heard of this because sometimes I get empty stares, but I did hear another reference to the Spring Boot Pet Clinic recently, so I know that it's still active. So this is Spring Boot is a Java framework for creating microservices. Very popular at my previous job. Over 50% of the microservices were Java Spring Boot. And this is a framework for doing this in Java. And if you look at the architecture diagram, there's a lot of things here. But at the core level, what the Pet Clinic is designed to do is manage customers, visits, and vets in a system. It has an API gateway that's taking HTTP requests, forwarding those requests along to the applicable microservice, which has a connection to a database. And then there's a lot of cruft over at the edge about like configuring load balanced HTTP requests and registering IP addresses and doing distributed logs and all that stuff. But the application itself at core is pretty simple. You can maybe see a little screenshot there in the middle. But what this looks like when you break it down in terms of capabilities and business logic is a little bit closer to this. You have an HTTP server and you have some kind of API gateway that's accepting HTTP requests and routing requests. You have a customers, vets, and visits microservice. These are WebAssembly modules in the wasmCloud land. And then they're all using the SQL database capability to interact with a SQL database. And specifically, I put in Postgres to kind of tie it down to a concrete implementation. But of course, this is still a capability abstraction. So what you just saw with the key value counter is a little bit more of a serverless function that you can invoke. This is a full stateful application that's composed of 4 different microservices and some capabilities. Now, let me show you what this actually looks like. If we go back over to Cosmonic, I've gone ahead and launched up this application ahead of time. And what I have, if I just rearrange this a little bit, is the full app running on Cosmonic. So the whole app is running in the cloud. We have user interface, our API gateway, and then visits, vets, and customers. So all pretty much the same setup. And taking a look at this application, let me go ahead and find it. You can see that it's actually pretty simple. We have a bunch of Cosmonic employees that are in here in the database, a couple of different vets that they can maybe visit, a couple of pet types that are managed, things like that. And deploying this to the cloud is good. Like we have our application, we have it fully hosted. This is kind of table stakes for where we leave things today. But when you think about not only just the edge of like your development machine, but when you think about the proper place for this application to actually run, it's probably in the vet clinic itself. It's probably on a smaller computer at the vet clinic. That way you can interact and manage customer data. If the internet were to go down, everything is local and can communicate data up to a central cluster. That would just result in quicker computers, quicker access to customer or vet data by being able to query a data store that's running locally in the center itself, things like that. So when we're thinking about taking cloud native applications to the next level, what containers and many modern applications struggle with is going to the edge. The Spring Boot Pet Clinic example, actually running not even a container, just as a Java jar, takes, I think it took me 1.5 gigabytes of memory just to run the application, which means running on a Raspberry Pi, kind of like this one that I have running here on my desk, is kind of a non-starter. If it is going to use 75% of the RAM just to run on a 2 gig Raspberry Pi, you're not going to have any room to run your database. You're not going to have any room to run anything else. So what I'd actually like to do is I won't do the full application just to make sure that we come in well on time. let me take a part of this so that you can actually see this working and migrate it to this edge device. So I held up the Raspberry Pi. I actually have it running at my place here in DC, and it's represented here on the canvas as a wasmCloud host. But what we can do is whenever we hit this endpoint here, we're hitting the customers microservice. We're hitting the API gateway and then customers. So I can actually take the API gateway. I can start an additional instance of that API gateway on a Raspberry Pi device. And then I can do the same thing with my customers microservice. I can start it on a Raspberry Pi. And then once that starts up, you can see we have another unmanaged instance here. And then, oh, I missed it. And then another unmanaged instance here. And if we go and hit the pet clinic again, everything, of course, is going to work all the same. But if we think of, if we're hitting this as a public endpoint, if we're running actually in the vet clinic itself, it may be better to hit it as a kind of a local host endpoint, like keeping it all routed locally in the vet office itself. What we can actually do is we can take this API and we can link it up to the local HTTP server, which we're running on the Raspberry Pi. And we can give it an address of something like 8083, something like that. Let me just double check. We have the HTTP server running on the Pi. So we did 8083. Now I'm going to change my screen share really quick. I should have done the full screen just to show this. Let's see. There we go. Got my terminal. I'm actually here just as SSH into my Raspberry Pi. What I can do is I can now curl my localhost 8083 endpoint and hit the customers. What is the endpoint? 1 second. There we go. Well, I know vets at least, but we can actually hit that endpoint locally on the Raspberry Pi because we now have an HTTP server running on the edge. So what I was able to do is essentially take an application that was running fully in the cloud, go from laptop to cloud, and then take the application from cloud to edge, which is really, really exciting. Let me go ahead and transition back to my other screen. So all in all, what you've been able to see today is, okay, that still worked. Taking this application and you can see the kind of flexibility that you get building it with WebAssembly and wasmCloud. So, if you avid stream watcher are wondering what can you do now, you can always use a framework like this for basic data image processing or function as a service style microservices. So things like taking an HTTP request, modifying some data is really efficient with WebAssembly and lends itself very well to the APIs and SDKs that are out there today. Where we've seen most people be the most successful in terms of getting the benefits out of WebAssembly is by essentially taking a strangler pattern approach. So take your full application, kind of take an audit, think about what could be running more efficiently in something that could be rapidly scaled, moved to the edge, or implemented in a more efficient way, and essentially take that out and implement it with wasmCloud. It'll run smaller and cheaper than it would running in Kubernetes. wasmCloud itself can run in a container or on a VM or in Kubernetes. It all works all the same no matter where it is. So you can essentially plug that into your existing architecture and infrastructure and run just a small part of a service. You can kind of do that comparison. And then, of course, if you're working in a fully greenfield space, you have the room to be able to experiment. You could write a full stateful application. At Cosmonic, I actually did a talk with one of my colleagues, Taylor Thomas, about how we dog food our own product at Cosmonic. So we wrote our entire backend in wasmCloud. And it's just a joyful experience. You can use the capability providers to connect to data sources that you need and state that you need to manage, all those things. So this is kind of a high-level idea of what you can do now. And if you're interested in what we've shown today, all of the capabilities in the actual demo is in our open source, which is here in Slack and GitHub. Please join. We do a community meeting every week on Wednesday at 1 p.m. Eastern time. So that's going to be in like 21 hours. We'll be live streaming again on the wasmCloud channel. But everybody is welcome to come join there and just come hop in the Slack. We'd love to chat. So this is the thing I included in the talk, I guess. If anybody has any questions, feel free to throw them in in whatever chat you're watching on. But that's the talk. Bailey, I think you're muted. Oops.
I am muted. Thank you, Brooks. That was awesome. That was as fun as the first time I saw it. So really great. I felt like it was a little bit, well, you're always a relaxed speaker, but it was chill too, I did notice on DevOps Day, people were just totally blown away by the UI, but I imagine most people that are watching it here on our stream, like that's all old hat at this point, and then you were able to, they were probably more focused on what you were actually saying, which is, hey, this is really, really powerful. A lot of people don't quite get what we're saying when we say, no, we used wasmCloud to build Cosmonic to provide wasmCloud hosted support for wasmCloud applications. The inception there never really, it doesn't really click until people start getting their hands on it.
Yeah, it's so fun. Well, hopefully this will be really useful. Of course, since we're streaming to YouTube, it's going to go up as a VOD right away. So you can kind of rewind, check out what I did, all that kind of stuff. And both of the examples that we have, actually, it would be pretty nice to get that as a caption. Let me see if we have it. All the examples are actually just open source on the wasmCloud examples repository. So the KVCounter and the code that I showed, and the pet clinic, the whole architecture and the code behind that, all of that is open source. So you can go take a look at that. And that is, I'll just go ahead and type that one out. Might as well. There we go. Yeah. GitHub.com/wasmCloud/examples.
And specifically the pet clinic.
Hey, nice. Even better. Well, Bailey, this was kind of your idea to hop on the stream and kind of do a talk recap, especially since we didn't get to, take what we did and turn it into something that was recorded. And so I'm really glad that we did this. Thanks for doing this and running through the talks again with me.
Yeah, thanks for hanging with me. I thought it was a good time. I hope everybody else enjoys it too. If you have any other questions, catch us over on the wasmCloud Slack.